All right, okay, let's get started. So we're going to continue today explore network structure and look at the different methods that allows us to explain it. What we're going to do today is we're going to talk about three different topics. We're going to talk about node similarity and node equivalence. Those are concepts. The concept of assortative mixing and the ways to compute it. And finally, we're going to talk about very special types of graphs, which are called bipartite graphs, and they're quite useful in the work you're going to do. So, we previously talked about global properties of the network, statistical properties of the networks, such as average node degree or node degree distribution, or average clustering, average path lengths. So that were the properties of the entire network. We then discussed local, what's called local vertex properties, things like node centrality, things like page rank. We then discussed, and it's not listed here, but we then discussed the way to cluster nodes to detect communities. And finally, we're going to talk today about the pairwise properties of the nodes. So when you have several nodes in the graph, how they relate to each other and how the properties of the nodes relate to each other. So the first property we're going to talk about is called equivalence. And the definition here, the idea is that two vertices are called structure equivalent if they connected to exactly the same nodes, right? Or if we speak more precise language, if their respective sets of in neighbors and out neighbors are the same. So if we look at this picture, then you can see, for example, if I look at the node, at this node U1 and the node U2, notice that they both connected to node V1 and node V2, right? And they're both pointing to those nodes. So in this sense, nodes U1 and U2 are structurally equivalent. So if we look at the matrix format, it really means that this is outgoing, outgoing links, right? That those two vectors are identical, and these are incoming links. Those two vectors are identical, where there are no incoming links. And so that's pretty much what it means to have structurally equivalent nodes. Now, this definition, though very simple and quite easy to check, right? You can actually go through all the pairs of nodes. Well, it's n squared, but you can still potentially go through all the pairs of nodes and check them for equivalence. The same way as when we talked about clusters versus completely connected group of nodes, it's the same idea. You don't always have exactly identical number of neighbors. And so you might want to relax a little bit this definition and look not only for structurally equivalent nodes, but for structurally similar nodes. Now, what does that mean? It is really about approximate equivalence. So if we look at this picture, you might realize that, for example, this node 29, has a set of 2, 3, 4, 5, 6, 7 nodes it is connected to. And node 26 has 1, 2, 3, 4, 5, 6 set of the node they're connected to. So they actually pretty much overlap significantly, right? So these are the common nodes. So from the structural perspective, these nodes, node 29 and node 26, they're not exactly equivalent because there are some nodes that they're not in common for those nodes, or neighbors not in common, but there are a lot of common neighbors. And which means they're not equivalent, but they're approximately equivalent, right? Or in other words, they're structurally similar. Again, structural similarity means similar connectivity pattern within the graph. And that means connected to pretty much the same nodes within the graph. So if I'm going to look at their actual metrics, because obviously if I introduce the notion of similarity, I want to introduce the notion of sort of some way to measure the similarity. The easiest way to measure it is, and it's actually probably the most popular, is what's called cosine similarity, where you think about every, when you take the vector representation where a node is as a vector, and the vector is a column or row in the matrix, and you just look for cosine of the angle in between those two vectors. And of course, if vectors are identical, which means nodes overlap, cosine is 0, so I'm sorry, cosine is 1, then they're identical, and if there is no overlap, cosine is 0. There is also very popular Jacquard similarity, which is in fact pretty much what we just discussed, which that computes Jacquard similarity, really computes, sorry guys. Too much security doesn't allow me to do things here. Okay, where you actually compute the number of, this is a neighbors, the set of neighbors of one node, the set of neighbors of another node, and we're looking for their intersection, and it's normalized by their union. And that also means that if you have a complete overlap in between neighbors, right, in between the nodes, then Jacquard coefficient, Jacquard similarity is 1, and if no overlap is 0. So these are two popular metrics. We can actually also compute what's called Pearson correlation coefficient, that computed the way it's shown right here. The idea is that, again, when you take product AIK and AJK, for example, and you look for the summation, it's non-zero on overlapping nodes. So all of these three metrics are used to define similarity. And they pretty much have the same sort of idea and similar behavior. The larger similarity, the larger is the metric. So when you look at the graph, and this is again our network, and this is that the karate graph network. We always looked at the adjacency matrix, right? Where the matrix, the non-zero elements would mean there is a connection between one node to another. So what we can also calculate is a similarity matrix, where the color coding corresponds to similarity in between nodes. So the way it's color coded here, it's it's monotone. It goes it's blue, white to blue, and so the diagonal is obviously the darkest. So the every node is similar to itself, so it corresponds to the value 1. And then there are some nodes that are more similar to others. One example which sort of obvious is right here. There is last two nodes, and in fact, this is node 33 and 34. If you look at them, the connectivity pattern is very similar, right? They're connected, both of them, they're connected to all sort of these nodes. These are nodes in common for those two nodes. And so they have structural similarity because of their connection pattern. And that's why this this one and this one are also quite, dark blue, right? Well, bright blue, right? And that's how you read this matrix. So pretty much every element that is darker of the diagonal, right? That means this node and this node are quite similar structurally. And well, I didn't put here node numbering, but that's obviously 1, 2, 3, 4. Again, 1, 2, 3, 4, and so on. Okay, does this make sense? All right, it's a very simple concept, but it's actually very powerful. Again, you cannot compute this matrix in a very large graph simply because this matrix is obviously n squared, right? Because there are n squared elements, and so it's a lot of computations. But on medium-sized graphs, you can actually quite easy to compute it, and then you can actually see which nodes in your graph are similar. And then when you try to interpret it, the idea would be that the similar nodes can perform, if it's a social network, can perform similar duties, right? Similar nodes means those two people have pretty much the same friends. And in the sense, they're sort of interchangeable, right? People, or within the, say, if you look at the structure of a company, then these people are, equivalent or very similar. If you look at the language, it probably means that these two words, if they are connected to, if the neighbors are overlapping, that really means if it's, for example, the connectivity network, then that really means that the words used in the same context, right? And so most likely they're synonyms. That's how we can use this, right? So that's a very practical tool. Next topic that I want to cover today is called mixing, or mixing on the networks. So what this means is that quite often on the network, we'll see, and especially with the social networks, you will see that nodes that have similar characteristics, they tend to be linked to each other. You can think a little bit in reverse and think about like how friendship occurs, how friendship happens. And you realize that often people sort of with similar beliefs or some other similarities become friends. It's very rare when people that are entirely opposite will become friends. You can also notice that quite often, people who are friends on the network, on social network, will have similar age. There will be the same similar age group, obvious reason. And in fact, it can be used to predict the age for somebody, who doesn't show his age. They usually similar income, right? And there may be very similar interests. Or like these days, they most likely even have similar political views. So, and that's called assortative mixing, this property, the tendency of the nodes with similar characteristic to link to each other, or the like links with the like, right? That's called assortative mixing. Now, there is the opposite of it, which is disassortative mixing. It's a tendency of the nodes with dissimilar characteristics to link to each other. Again, assortative mixing could be even, by number of friends. It's usually popular people connects to popular people. It's very rarely when a popular person will connect to some loser who doesn't have any friends, right? Or again, rich friends with rich, poor friends with poor. It's rarely when rich are friends with poor. So in social networks, you usually see assortative mixing, but sometimes in the world, we actually also see disassortative mixing. An example of disassortative mixing will be typically, if you think about, marriage, right? And married couples, that will be usually of opposite sex, not always, but usually. And that actually is that if the nodes are people and ages are marriages, then, here you get disassortative mixing with respect to the sex, right? Okay, with respect to gender. So the quite interesting picture is, I want to show you quite interesting picture. This is This is 10 years ago. These are political polarization on Twitter. And this shows retweets by sort of right-leaning and left-leaning users. So it's actually Republicans and Democrats, literally self-identified Republicans and Democrats, and how they retweet each other. And so it's very clear that Republicans listen only to Republicans, Democrats only to Democrats. And back then, there were more sort of Democrats in the Twitterverse. That was before Mr. Trump times, right? I'm pretty sure that now, if somebody measures this, I'm pretty sure there will be papers on this, the picture is even more polarized, right? In a sense that, again, red is retweeting red, blue is retweeting blue. So according to our definition, is this assortative or disassortative situation?
Assortative?
Assortative, right? So it's liked, connected, or likes, retweets, likes, right? So red retweets red, blue retweets blue, and it's very rarely when red retweets blue or other way around. There is also another word for assortative mixing. It's called like homophily, right? So that's another terminology for it. So the sort of similarly to what we talked previously, whenever we talk about different type of metrics, you want to actually measure this numerically, and there is a metric of assortativity. Now, there are two kind of metrics. One is we can actually talk about categorical attributes. So things like gender, things like, I don't know, race, things like you think of, right? Or if it is language network, it could be nouns, pronouns, whatever. So this metric measures how often attributes across the edge matches, how often the matches compare to if the network was random. So think about the same network with the same nodes, the same labels on the nodes, but then connected randomly. So if it is connected randomly, we assume that it's sort of neutral. There is neither assortative nor disassortative mixing, right? So on average, there will be sort of equal number of edges connecting opposite types versus and similar types. So here the idea is to contrast your current network, current arrangement, current structure versus that hypothetical random structure. And that's called the assortativity coefficient. And that's just how it is computed. Again, you don't need to type it to put it in. There is of course built-in command. And then if we want to talk about scalar values, for example, age, maybe income, if you think about social network, then it's really correlation coefficient, but it's not just simple correlation coefficient. It's the idea that we only measure correlation in between values of the nodes that are connected. So usually you would measure correlation if you want to say, calculate some correlation coefficient, you would measure it in between all the possible pairs. Here, you measure it only in between nodes that are connected. And then the idea, if in between nodes that are connected, if, for example, node with large value connected with a node with large value and node with small value connected with a node of small value. So that's called, that's correlation coefficient, that's assortativity metric when you have scalar values. Finally, we can actually think about this, since we can introduce this assortativity property with respect to all kind of node properties, right? Like labels or values, we can also use number of connections of the node as that property. So you can think about nodes with a lot of friends connecting with the nodes of a lot of friends, or node with a lot of friends connecting with nodes with fewer friends. So that's going to be, it's called mixing by node degree. And you can have assortative network with respect to mixing by node degree, and disassociative. And there is a very clear distinction between them. In assortative network, you will have low degree nodes connecting to the low degree nodes. And it's clear here, right? So like most of the time, low degree nodes connected to low degree nodes. And somewhere there, the probably like, densely connected node connected to densely connected node. In disassociative network, it looks quite often as a tree. So you have, big node, and then there are a bunch of branches connected to it, right? You have a node of high degree, and then a bunch of nodes connected to it. So this is an example of disassociative, that example of assortative network. Okay. So we again can measure that, and it's the degree of assortativity with respect to node degrees is measured by what's called degree correlation coefficient. And here's the formula. Again, it's really the correlation coefficient where you use node degrees. And if it's greater than 0, you get assortative network. If it is close to 0, you get neutral. If it's less than 0, you get disassociative network. And here is an example. So the way to understand this is the following. If we look at this picture, this picture is done for 2 nodes because the correlation is a pairwise property. And so on the vertical axis, we have the degree of one node, K1. And so this, for example, node with 5 neighbors, 10 neighbors, 15 neighbors. And this is a degree of another node, right? 5 neighbors, 10 neighbors, 15 neighbors, 20 neighbors. And what this shows by color coding is that, for example, here you have dark colors, which means, nodes of high degree, 15, more often connected to nodes of degree 15 than, for example, of degree 5, because here it's light, right? So that's those nodes. And on this part of the spectrum, mono usually nodes with low degree connected with nodes of low degree. And of course, it's darker in the center, which means, majority of the nodes in your graph will, say, be around degree 10. And yes, they will be connected to the same type of nodes. And we have disassociative network. The situation is opposite. You get high degree nodes connected to low degree nodes. And that's what's happening at both ends here. Here is one node of the high degree, another node of low degree. Here is again one node of high degree, another node of low degree. And if it is neutral, that's what it looks like, sort of. It's sort of two-dimensional Gaussian, right? And again, this sort of degree correlation and association by node degree, it's very clearly, it can be very clearly observed if you look at the network, right? Assortative gives you a sort of chains and then dense center. Disassociative gives you sometimes like, tree-like structure, or, pictures like here, and, neutral is usually, it looks quite random. Any questions on this? Okay, moving along. The last topic for today, and we'll have quite short lecture, is called bipartite graphs. So what does it mean? Formally, a bipartite graph is a graph where you have 2 types of nodes, and where only nodes of one, where nodes of one type only connected to nodes of a different type. So it's usually what's called 2-mode network, bipartite graph. And that means you can split nodes into 2 types. And these are 2 types. So those 2 sets are disjoint. So if we look at this picture, notice that nodes from the set U only connected to the nodes with set V, and there is no connections in here, right? So, where do you meet this net? How often do you meet these networks? It's actually a lot of networks that we deal with are actually originally bipartite networks. You can think about this, for example, again, with marriage, it's not going to work anymore, but you can think about, say, customers, right? This is the customers. And let's say these are, I don't know, books or items they actually buy, right? And so every edge here means that, customer from the set U bought an item from the set B. So customers don't buy customers, and items don't buy items. So so you don't have that connectivity within each of the groups, but you do have cross connectivity. Okay. Or another example, one set can be authors, and the other set are papers that those authors wrote. And then the interpretation is actually quite easy. Let's say if this is a paper, that means there is this 3 guys wrote this paper. But then this guy also authored another paper with somebody else. That's fine, right? So that's how it works. And that's why these bipartite networks are often used to describe, those type of systems. In fact, again, this is called two-mode network or bipartite or bigraph. In fact, there exist tripartite networks, so 3-mode networks, 4-mode networks, etc., where then you would have just, say, tripartite network, you'll have 3 groups of nodes, and it's only cross-group connections that are allowed, right? So you can think about, I don't know, professors who are connected to papers and students who are connected to papers and professors, right? And so these are 3 different groups, and then there is no connection, say, among them, but there is a cross connection. So now, how do we deal with these networks? Well, the one trick is that you can actually work with them exactly the same way as with any other, as a sort of unipartite network, right? You can completely ignore the fact that there are 2 types of nodes. You can sort of close your eyes onto that and run exactly the same algorithms, exactly the same clustering algorithms, exactly the same, centrality. I mean, anything you want. And then when you're done, you can sort of recover the fact that there are 2 classes of nodes in there. So the fact that these nodes of 2 classes does not prevent any algorithm to operate in this network. But there are some additional algorithms that can be used, based on the fact that these are bipartite networks. Actually, example, it's also called affiliation network. I should have switched to this slide before, but yes, there is a candidates and jobs when you do job applications. There are authors and papers, directors and boards, advertisers and the keywords they advertise on. There are actors and movies, people ratings. So it's called affiliation networks because it quite often talks about affiliation of people. It can also be people belonging to different groups, etc., etc. So here, this picture is actually a board of directors of different companies, how the same people are sitting on different boards. Now, there are several properties I mentioned. This is, in fact, also a bipartite network. I did not show, I mean, I could have redrawn it this is the way I've shown you before into this, having these 2 columns and connecting them, but it doesn't have to. This is a bipartite network. Why? Well, it's because if you look at it, it's only, purple connected only to this greenish node, right? And there is no green connected to green or purple connected to purple. But otherwise, it's just normal network. And there are a bunch of properties, mathematical properties, like, for example, it can be vertex colored with 2 colors, which means you can have this alternating coloring, which makes it bipartite. Or, for example, because of that, it does not contain any odd length cycles, right? So any cycle that this network can contain can be only even numbers. One can prove it on this picture. As you can easily see, it's like 4 node cycles, right? But 3 node cycle is impossible because if you try to make it, you will inevitably connect nodes of the same color, which you not do, right? And so there are many other sort of interesting properties that bipartite graphs have. You can investigate and use. It's also good to notice that when you have bipartite graphs, they're naturally represented as tables. This is not an adjacency matrix. It's a table, which means you have one type of nodes, sort of one type of nodes shown along one dimension and another type of node shown along another dimension. So here, this is, we have advertisers, and here we have, types of sort of keywords they advertise upon, right? These are those keywords. And so it's, traditional sort of think about Excel spreadsheet, and then anything that has rows and columns can be thought of a bipartite graph, connecting this type with that type. Make sense? Okay. All right. So, but the most important property in bipartite graphs is the following property, and that's the most useful. It's called a one-mode projection. So think about the following way. Let's say our bipartite graph is about, authors and papers they wrote. So that's, say, our graph, authors and papers. What you can do is the following. You can actually, based on this graph, you can build a co-authorship graph where two nodes are connected if those two people, so it will be graph only of authors, and the two nodes will be connected only if the people author the paper together. So we take A and B, they author two papers together. So there is a connection here, and actually can carry weight too, because they author two papers together. But then there is A and C. They don't have any common papers, so there'll be no connection. There is B and D. Well, there is one common paper, there is a connection. So you can build this co-author graph. Or you can also build a graph of papers. You can say, look, two papers are connected if they have an author in common. So paper 1 and 2, they both have got author A in common, and so they're connected with weight 1. Paper 2 and 3 have A and B in common. So both of them had author A and author B writing them, so that there is a weight 2. And so on and so forth. But say 1 and 5 is not connected because they haven't been co-authored. All right. And so these things are called one-mode projections. There are two of those. And technically speaking, the way to do it is very easy. You just take matrix, the adjacency matrix. I'm sorry, this our table, and then you do this table time its own transpose, right? So you can do it either B transpose or B transpose B, depending on how you put it. You either get this projection or another projection. Okay. And that's pretty much all the stuff I wanted to cover today. You're going to use this in the class later on. Again, this projections, they are actually quite powerful and used a lot. And there is operators in network X to do this one mode projection. And as always, there are papers, and you can dive in. And that's it for today. Questions? Okay, this was a quite easy lecture. So I'm not surprised that there's no questions. Let me stop the recording.